Good morning, everybody. Welcome back to Abstract Algebra. Plan for today, we're going to finish our packet we've been looking at on rings. As far as office hours go, I've got my usual ones. Today at 2, tomorrow at 10 in the morning and at 1:30, and Wednesday, hour before class, and at 2. As far as homework goes, exam 2 is going to be sent out Wednesday. And just like the first one, you will be allowed to work in pairs. Though you do have to submit your own write-ups for the exam, so I'm going to think about who you want to work with and get that set up. So where it's going to go. Exam 2 is going to be it's going to be like exam 1. You're going to have a week to work on it. I'll send it out Tuesday night / Wednesday sometime. It'll be due the following Wednesday night. And it's going to focus on the topics covered since exam 1. So to give you a sense of what topics those are, it is iso/homomorphisms, cosets, Lagrange's theorem, direct products, GAG, the fundamental theorem of finite abelian groups, normal subgroups, quotient groups, and the first isomorphism theorem. I'm not going to include anything about rings on this exam. Instead, what's going to happen is the final is basically going to be just all about rings. But these are going to be the main topics that are focused on exam 2. Not to say you won't need to know anything about cyclic groups or subgroups or any of that, but those are kind of exam 1 topics, and everything I ask is going to have something to do with at least one of these. Any questions about the exam? COVID. If you haven't noticed, we went from 61 COVID cases on Friday to 97 this morning.
What?
I know. That's not good. That is bad. There is a good chance that I'm just going to move this class online. It's going to be in person until further notice, but do not be surprised if all of a sudden we're online on Wednesday or Friday or whatever. I will send an email out with information when that happens. If that happens, I haven't decided what the format will be, whether it's just I continue recording on my own and submitting to YouTube and doing some sort of group office hours, or if we do like group Zoom sessions at 11 o'clock Monday, Wednesday, Friday. Haven't decided yet. Need to think about that. We'll let you know if / when we go online. But that's currently the plan, because this is getting out of control fast. I'll get this like triple the number of cases in the last week and a half. And that is not good. Plus, as you can see, lots of students in quarantine. Does anybody have any questions or comments before we get started for today? Yes?
Is exam 1 graded or not?
Wrong question.
It's still in progress. It's gonna be finished by the time exam 2 gets out, I promise. Okay, yeah, there's a lot that happened this weekend, both with COVID stuff and politics stuff and other classes stuff and family stuff that made it so all my plans to finish grading exam 1 this weekend got dashed. I apologize.
Sorry.
That's a personal failure, but, and I know this class needs to be graded much faster than it has been. Don't tempt me. But yes, I will. But no, exam 1 is not finished grading yet. Some of you could probably, some of you have submitted final homework exam scores for, so you might look and just see if I submitted. But if I haven't submitted by now, it'll be submitted by Wednesday. If I have to stay up all night on Tuesday, it will be submitted by Wednesday. Any other questions or comments? Okay. What the heck? This is not the right page. Give me a second. All right, here it is. A chemist, an engineer, and a mathematician stumble upon a pile of beer cans one day. They're excited because they want to get drunk. Silly scientists. Unfortunately, they're the old-fashioned cans that don't have the little tab at the top. So one of them proposes, all right, let's go split up and find a can opener. We'll meet back here. The chemist goes to the lab and concocts a chemical that dissolves the top of the can in an instant, but then immediately evaporates so the beer is not affected. The engineer goes to her workshop and creates a new hyper opener that can open 25 cans a second. Quite impressive. So engineer and chemists are pretty smug with what they've done. They go back to the pile with their inventions and find the mathematician finishing off the last can of beer. They ask the mathematician in astonishment, how did you do that? She responds, oh, that's easy. I just assumed that they were open and started drinking. Okay, so last time we were talking about rings, where we said that a ring is a set R with two binary operations, one which we call addition, one which we call multiplication, where we said the ring has to form an abelian group under addition. It has to have closure until under multiplication, meaning if you multiply any two things in the ring, you'll always get back something in the ring. Multiplication has to be associative. And finally, we want these distributive properties, that if you add two things, a plus b, and then multiply by some c, that's the same as taking a times c plus b times c. And a times the quantity b plus c, we always want to get a times b plus a times c. And if you had all those things, we get a ring. Last time, we looked at a bunch of examples of rings and non-rings and talked about some properties that rings have to satisfy. In particular, we showed that if 0, which we're always going to call the additive identity in the ring R, and 1, which will always be the multiplicative identity, if it exists, in a ring R, we said that if you multiply anything by 0, you're always going to get 0. Was what we proved at the end of last class, which is the same as saying, which tells us then the only ring that forms a group under multiplication is going to be the trivial ring, the ring with only a single element in it. And today I thought we could start off by looking at another theorem, which is the one part that says that if we take -1 and multiply by any element a, we're always going to get the same as -a for all a in our ring R. Dr. Gerstle, isn't this obvious? -1 times a is -a? It's somewhat clear, but not entirely obvious, because it's not exactly clear what exactly do we mean by -1 and -a. So can anybody remind me, what did we say was the relationship between, or how do we define -a? If a is some element in our ring, what is -a going to be? The additive inverse of a. Bingo. So this is going to be the additive inverse of a. I.e. the element such that -a plus a is going to give us 0. It's the thing you add to a in order to get to the additive identity. And then -1 will just be that, but for 1, where 1 is the multiplicative identity. And so our theorem is really saying if you take the additive inverse of 1, and if you multiply by anything in the ring, you're going to get the additive inverse of that element within the ring. Which, when you put it that way, makes it maybe seem a little less obvious than just saying -1 times a is -a. Because our multiplication and what we call negatives of things aren't necessarily the multiplication and the negatives that you're used to thinking about with real numbers, for instance. So let's see if we can prove this. my exam 2 topics, I hardly meet. So we're going to let A be an element in R to start. And we'd like to show that negative A is equal to negative 1 times A. How can we do that? In particular, if negative 1 times A is equal to negative A, what equation would negative 1 times A have to satisfy? So in other words, negative 1 times A equals negative A means this equation is true. Or negative A is the thing that makes this equation hold true, that x plus A equals 0, negative A is the solution to that. So if negative 1 times A happens to be equal to negative A, then what equation could we set up that would have to come out, that would have to be true in order for this thing to be equal to that thing? Okay?
Negative 1 times A plus A equals 0?
Bingo. If this thing is equal to negative A, then we should be able to substitute negative 1 times A into this equation for negative A, and we should be able to get 0 out of that. And if that happens, if negative 1 times A plus A always gives us 0, then it would have to be the case that that it's equal to negative A, because negative A is defined to be the element in our range that satisfies this. So if we set that up, we'll get negative 1 times A plus A. And we'd like to be able to show that this is going to come out to 0. We'd like to be able to use the properties of our ring somehow in order to make this happen. That if we were to take negative 1 times A and add it to just plain old A, we'll end up with 0. So what would be a way that we could rewrite this in a way that'll get us to some way in order to combine these two terms into a single term? I'll give you a hint. One thing we can do right off the bat is just replace A with 1 times A, because by definition of 1 being the multiplicative identity, 1 times any other element in our ring should just give back that other thing in the ring. So 1 times A is A. What would be a way that we could sort of try and combine these two things into a single term using one of our ring properties? Right? Yeah, we could use the distributive property. So what would be a way we could rewrite this using the distributive property?
A times negative 1 plus 1 in parentheses.
Negative 1 plus 1 times A.
Okay.
Don't forget, multiplication does not have to be commutative in our group, or the same group, in our ring. So hesitant to just swap the order of those two terms like that. Addition has to be abelian, or has to be commutative, but multiplication doesn't necessarily. Like if our ring, for instance, is the ring of all 2x2 matrices, then in that would be a ring where multiplication is not commutative, so you couldn't just swap things all willy-nilly like that. But you're right, we could write this, we could use the distributive property, specifically this first one here, say negative 1 times A plus 1 times A is going to be the same as negative 1 plus 1 times A. What's negative 1 plus 1? Third grade math class.
0.
It's 0 by definition. Not because the integer negative 1 plus the integer 1 is 0, but because of this equation. Negative 1 is defined to be the thing that if you add to 1, you get 0. Therefore, if you take negative 1 and add it to 1, you get 0. And what's 0 times A going to be? 0. Not obviously, this is not obvious that 0 times A has to come out to 0, but that's because of the previous thing we proved at the end of last class. or the fact that 0 times A came out to 0 was also a result of using the distributive property. So negative 1 times A plus A does in fact come out to 0. Hence, by definition, negative 1 times A must be equal to the negative of A. Something that looks very obvious. Yeah, Dr. Ursel, duh. Negative multiplying something by negative 1 is just taking the negative of that thing. But in fact, does rely on the distributive property. Because if we didn't have the distributive property, these would not necessarily have to be equal, and all our intuition about how negative numbers works would go flying out the window. But distributive property gives us this nice thing happen, which is one great reason why in rings we would love to have the distributive property, is so that everything intuitive about how we feel multiplication and addition should work will still have to work within a ring. Any questions or comments? All right, so there's a bunch of other general ring properties on the last page. I don't know. Don't be surprised if one of them shows up on the exam. I still need to write the final exam. This stuff will not be on the, just as a reminder, rings will not be on exam 2 at all. Rings exam 2 is going to be second half of your stage. But don't be surprised if one of these parts of this theorem does show up on the final. So next thing I want to talk about is subrings, which you can probably guess exactly what a subring is. It's a ring living inside of a bigger ring. So specifically, we can say that if R is a ring, S is a subset of R, then S is a subring of R if S forms a ring under the same operations as R. So, classic example would be if our ring is, let's say, the integers, what would be an example of a subring of the integers? Something that's still closed under multiplication, addition, and all that, and also is in and of itself going to form a ring. Here?
Would be the even integers?
2z?
Yeah.
Yeah, I think 2z should work. How about 3z? That one? I think ng in general, yeah, is always going to be a subring of the ring of integers. Because nz will end up satisfying all 4 of these properties. So here's something interesting to note. The multiplicative identity of the ring of integers is just going to be 1. Let's say our n is, 2. So if we were looking at the subring S of, and say, if S is, say, 2z, which is a subring of the ring of integers, what's the multiplicative identity in 2z?
Is it still what it was in just the general set?
So 1?
Yes.
So you claim the integer 1 is going to be the multiplicative identity in the ring of all even integers?
No.
You don't claim that.
I'm confused now. I had something, but I no longer have something.
Ain't that disappointing?
It is.
Such is life. It
Well, it doesn't have to have one.
doesn't have to have one. I would say in this case, S does not have a multiplicative identity. And that's something that's totally okay for rings to have. I think all the rings we've seen so far have multiplicative identities. This one, S does not. And in general, NZ will not unless n is plus or minus 1 or 0. But those are boring examples because that's just either the integers or the trivial ring. So nowhere on our list of properties do we require that R has to have a multiplicative identity. It's very well possible that you can have rings like this that don't have any multiplicative identity at all. You always have to have an additive identity because that's part of having R form an abelian group under addition, is that you have an additive identity and additive inverses, but you do not necessarily have to have a multiplicative identity or multiplicative inverses in order to have a ring. Any questions or comments? Yeah, Peter?
Is there a specific symbol for like the subring or like later?
Not really.
No.
Not really. It's got usually the problem with trying to use like this symbol for subring is if I were to say something like this, what am I saying? Am I saying that S forms an additive subgroup of R, or does S form a subring of R? Or does S form an ideal of R? But we haven't talked about what that is yet. Problem is, it gets a bit ambiguous, so we don't use this symbol typically to refer to subring. You may have noticed I started to write that out here and immediately erased it because I'm so used to thinking, oh, something else, that's just the less than or equal. Not in this case. So usually you just kind of have to say it's a summary of that. A little bit unfortunate, but there's not like as much a common symbol that's used as there is for subgroup. All right, good question though. So, to give you a quick theorem, there is a nice theorem that tells you exactly when a subset is a subring, and this is the subring test. Subring test says that a non-empty subset S of ring R is a subring if and only if, I think it just says if the following hold, it should say if and only if. First is that S is closed under subtraction. So in other words, for all elements A and B in your set S, A minus B has to also be an element in S. And the second condition that's necessary for a subring is closure under multiplication. S is closed under multiplication, i.e. for all A comma B in S, A plus B has to also be an element in S. Piece of chalk. If you have both these conditions, then you have to have a subring. If you're lacking at least one of these two conditions, then you do not in fact have a subring. So here's a question. Why did we say subtraction and not addition? Maybe we should start actually with a quick reminder. What do we mean when we say A minus B? That's not one of our operations we defined as part of our group. What was A minus B?
That's like A and the additive inverse of B.
Yeah, so A minus B is just defined to be A plus negative B. So we're basically saying we need S to be closed under subtraction, meaning basically given any two elements in your group, if you add one element to the additive inverse of the other element, we always want to get something in our group. And part one of this theorem is actually a theorem in and of itself that we've seen before. This right here is the one-step subgroup test. Because if you remember, the one-step subgroup test is H is a subgroup of G if and only if for all A and B in your sub thing, A times B inverse is in your sub thing. It's just that A times B inverse really just means the same thing as A minus B if your group operation happens to be addition. So really, saying S is closed under subtraction is just meaning that property 1 holds for having a ring. That R comma plus has to be in a Boolean group. This means it's a subgroup. S is a subgroup of R under addition. And then condition 2 here, condition that says S is closed under multiplication, that's just saying it has property 2. But Dr. Gerstel, what about properties 3 and 4? Properties 3 and 4 of having a ring will always hold true as long as S is any subset of R. Because since multiplication is associative over all of R, it's automatically going to be associative over any subset of R. Basically, because if you take, any A, B, and C and elements of S, they're also going to be elements of R, and so the associativity equation will hold true there. And the distributive properties will similarly hold over any subset of R, because if you take any three A, B, and C and S, they're going to satisfy these equations, because A, B, and C would also have to be elements in R as well. So really, the subring test is just telling you the only things you need to check for S to be a subring of R are these first two conditions. In this first condition, you can get from just using the one-step subgroup test. And I guess the fact that it has to be addition has to be commutative, that R is an abelian group under addition specifically. The commutativity is again just something that comes from S being a subset of R. Meaning if A and B are any two elements in S, they automatically are going to be elements in R, so A plus B will have to give you the same thing as B plus A, just because of that. So basically, this just comes down to the one-step subgroup test in part 2. I kind of gave a very, very informal proof without writing anything down, but is everyone okay if I skip proving this formally? Cool. Awesome, possum, a lemon blossom. All right, so you all know the drill. Bottom of this page and on the next page, I'm going to give a bunch of examples of potential rings and subrings. I would like you all to take a couple minutes working on your own and see if you can determine which of these form as subrings and which ones do not. And yes, if you don't have a packet, I will write them down on the board. Go ahead and take just a couple minutes. Take a look at the rest of this page and the next page and see which ones you think are going to be subrings and which ones you think are not. I'll give you a hint. The first one totally checks out. I'll give you a hint for this last one. Check out the second page of the packet. So C of R is a set of all real functions that are continuous over the reals. And S is going to be the set of all functions that are continuous over the integers. Oh no, Dr. Versal, what a horrible real analysis example.
You don't think you're here? You think
This
you're
one
here?
was, this one was, it's not. Is that actually
Is that how we define the complex?
I just think there's a lot.
Oh, but they're all integers in this case. Well, integers minus integers are gonna be integers.
Yeah,
well, are they-
The integers or the picture of the.
Well, it says A, B, or.
I'm sorry, distracting noises are perfect.
Yeah, when you do like the picture on the board.
It says
so
right here
many
that A,
A,
B, are integers.
like a little
Are
circle
those
with this.
ABRs or maybe they're referring to-
Yeah, so like if R is like a big ring, S would just be a smaller ring living inside of the big one,
Yeah.
in order for S to be a subring.
Oh, no, A is an A plus B.
That one is, yeah.
There was like, you could smell natural gas in that room.
Yeah, I think that's a new physics professor over there. I think that's Dr. Lawbeck. She's running experiments that are going to kill us all.
It's just trying to make deal.
Yeah, the.
I was on her hiring committee. Maybe I should. I knew she was going to be up to in here. Maybe I should have written this.
I was gonna say, better screening process.
I'll keep that in mind. Go ahead and take a couple minutes and think about these, and we'll come back together as a class once you've all had time to take a look at some of these.
Yes.
Yes, for this.
I said yes.
Because like if you got Z
I feel like the,
on 10, first of all, what happens when
I didn't know for the last
you
one.
multiply 9?
Like,
Nine.
because the output has the
What happens when you
integers,
subtract?
so if you
Yeah.
subtract
Yeah.
1 and 5, we'll have, yeah.
Yeah, 6 now.
That's what I was thinking. It's just not.
Why?
Okay, the next one, I said, yeah. Is the zero matrix in the set of L2 by 2?
Okay.
Zero matrix is definitely going to be in both S and R in this case.
Okay.
Mainly because zero is in fact an integer.
Nice.
Fun when that happens.
Yeah. Well, I mean, if you multiply them, you're gonna get another 2 by 2.
Murphy's left his laptop. Way on.
I said no for the next one.
Do we know?
Because there is,
I'm not actually going to try that.
Polynomial degree
Dr.
n
Murphy,
times
1, 2, 3.
polynomial.
Me too.
Dr. Murphy, 1, 2, 3.
Not necessarily.
IT department needs to have a talk with him, but that's his password.
It's not close enough multiplication.
That's, yeah, hacking other professors' laptops is definitely the sort of thing I should leave for after tenure.
Yeah.
Which one?
Or just students.
Or just what?
Or just your students.
Students, that I could do.
Yeah.
Does it have to be?
No, when I was a student, I hacked another student's computer. That was fun.
I just don't like that. Only getting one now.
I feel like I'm in trouble for it. That's less fun.
Yeah, I don't. I guess it can't be a subring if the first part.
Just all the numbers are like that. Not five.
Now this terminology with Z and then I in brackets is going to be something we're going to talk about in the future packet. And for now, just think about it as being complex numbers whose
This one.
real and imaginary parts are both integers.
Right, yeah. No, I don't think it's possible. And then the last one, I have no clue. So this isn't a ring, right?
Yeah.
So then obviously this can't be so. Okay. I'm looking at the last one. And why?
I'm just like, the output is gonna be an integer. So the output has to follow subtraction multiplication.
Oh. Okay. I'd buy that.
All right.
Buy that for one integer dollar.
Let's do another about another 30 seconds, and then we'll come back together.
Wait, why did you say the top one?
Yeah.
Why? I didn't think it was closed under multiplication. Oh. Well.
Well then, I guess that shows me.
But what happens when you take 9 and multiply by 9?
Madness.
You just continue to mod by 10? Oh,
All right, let's take a look at these, some of these. So first example I want to look at is our ring R is the ring of all complex numbers, and S is going to be the subset of that, where we only look at complex numbers with integer, real part and imaginary part, where A and B are both integers specifically. So something like pi plus square root of 2 times I would be in R, but not in S. So by show of thumbs, thumbs up for subring, thumbs down for not a subring. 1, 2, 3, vote. Everybody pretty confident this one's a subring? I agree. So we can even do a quick proof using the subring test by just taking two arbitrary elements in here and showing that their difference and their product are both in S. And we can say for any A plus BI and C plus DI elements of S, if we were to take their difference, if we were to take A plus BI minus C plus DI, what would we get if we subtracted those two complex numbers? Let's see. I remember, who do I know is in complex analysis? Class. Oh, hey, well, what a coincidence.
A minus C plus B minus D times I.
A minus C plus B minus D times I. And is that going to be a complex number whose real and imaginary parts are both integers?
Mm-hmm.
I'd say so. Since A, B, C, and D are all integers, A minus C and B minus D are both going to be integers. So this is going to be an element in S. And if we took the product, A plus BI times C plus DI, we're going to get what? AC minus BD plus BC plus AD times I believe. If you FOIL that out and use the fact that I squared is -1 to say BI times DI is going to be BD I squared, which is negative BD. And if A, B, C, and D are all individually integers, is AC minus BD and BC plus AD going to be integers? Indeed. So by the subring test, we know S is going to be a subring. S, by the way, it's going to be a subring with a fancy name to it. We're going to call S the Gaussian integers. I guess technically the set of Gaussian integers, which are basically, the Gaussian integers are just going to be complex numbers whose real and imaginary parts, the A and the B, are both integers like this. Depending on how far we get, Gaussian integers are going to be an interesting example to look at in a few weeks down the line.
What's so special about them? They got their own
Because Gauss studied them. It becomes, you get a lot of interesting questions in that you can ask some interesting, and you can ask a lot of interesting questions about this set, like what are going to be the prime integers in this set? What do prime numbers look like in this set? And what do irreducible numbers look like in this set? That sort of thing. Yeah, we're going to be talking about prime numbers and why what you all think are prime numbers are not actually prime numbers. How about this one? Our ring is the ring Z mod 30Z under addition and multiplication mod 30, and S is Z mod 10Z under addition and multiplication mod 10. By show of thumbs, thumbs up for ring, or thumbs up for subring, thumbs down for not a subring. Vote in 3, 2, 1, go. Some controversy. Megan, I don't know what this is supposed to be.
That's what you mean, like, I have no idea.
You have no idea. Refuse to vote. Okay. Steve, you vote no?
Yes.
You voted yes. Why did you say yes?
Based on a rotation
Ah, so you're saying these are both rings, so clearly it has to work out? Fair enough. Someone voted no. Show of thumbs. 1, 2, 3, vote. Kelly, you voted no. I thought you know to vote to change your vote after that. Why did you say no?
I kind of think it's not closed under subtraction, but I also could be wrong because quotient groups.
Ah, yes, they're sneaky buggers. I think S is going to be closed under subtraction mod 10. So
It's not 30.
it's not what?
It's subtraction.
Oh my gosh, it's defined differently. And this is one of these sneaky things where it turns out to not be the case. S is not a subring. S is a ring, and R is a ring, but S is not a ring under the same operation as R. Because S is only a ring under addition and multiplication mod 10, and whereas R is a ring under addition and multiplication mod 30. So that was me being sneaky, as an example. R is the ring of all 2x2 integer matrices. S is the ring of all 2x2 integer matrices whose top right and bottom left entries are 0. By a show of thumbs, subring or not subring? 1, 2, 3, vote. Do I feel pretty good about this one, it looks like? Yeah, check that. I really feel like it. But you could use the subring test and check fairly quickly that this works out. Just take two matrices of this form, show that if you subtract them or multiply them, you're going to get other matrices of this form. R is the ring of all polynomials of degree less than or equal to n plus 1. S is the ring of all polynomials of degree less than or equal to n. By a show of thumbs, subring or not? 3, 2, 1, vote. Dave, why do you say no?
Because R is not.
Oh, neither of these are rings. Yeah, because these are not closed under multiplication. So neither of these are rings. You could say that S is a subgroup of R under addition, but it's not a subring because neither of these actually form rings. And finally, how about this one? R is the ring of all functions continuous over the reals. S is the ring of all functions continuous over the integers. 3, 2, 1, vote. Solid amount of thumbs up, a solid amount of no votes.
Sorry, Bob.
Is that a continuous function? F of x is defined to be 1 if x is an integer, 0 if x is not. I'll graph it for you. Think back to Calc 1. Does that look like a continuous function over the reals? Does that look like a continuous function if you're only considering your inputs to be integers? Turns out it is continuous over the integers, because over the integers, this is just a constant function, y equals 1. You plug in any integer, you get 1 as an output. If only things you're allowed to plug in are integers, then this is continuous. But if you're allowing yourself to plug in real numbers, then you could say, no, this is very much discontinuous at all integers. So basically, f of x is an element in S, but not R. So S is not a subset of R, and hence not a subset. We're not going to look at this example much more. This is a very real analysis flavored example, and I'll let you take real analysis with these sort of fun things. Dr. Gerstle, what is continuous? I don't know, something with epsilons. We don't do that in here. Any questions or comments, though, about these examples? So try to pick some that have sneaky reason for not being a ring, like, or not forming a subring, like neither is a ring. The ring's under different operations. Oh my gosh, that's too scary, Dr. Gerstle. Don't make us look at that again. But in general, you need subtraction and multiplication in order to guarantee a subring. All right, that's going to do it for today. Next time, we're going to talk about ideals, which are a special form of subrings that's going to give us some interesting properties to it. Hope you all have a good rest of your day. I will maybe see you on Wednesday. If you don't hear from me between now and Wednesday, we'll meet in class. We'll meet in person Wednesday. Otherwise, we're just you'll hear from me otherwise. Have a good one.